are loaded, things like that. The naive way is to just record all the registers and any access memory after each instruction. That's, I mean, just thinking about it makes you cringe. How much would you be spitting to disk doing that? How much time would you spend doing I/O? Now, the guys at MSR came up with, they wrote a really good paper on this. It was the Nirvana project. So they have this reversible debugger. I mean, I guess GDB has something that does this now, but not the same way. The Nirvana project will take an entire trace of a program, and then they have these plugins that allow you to go backwards and forward in the trace to do a debug or to do, I mean, you could write BaSO4 on top of that, but it's also good for debugging. So they described their method for doing this. And they maintain a whole shadow copy of memory and registers, and they actually emulate most of the integer instructions along the way. And then before they decide whether or not they're going to write out the new modified registers, the new modified memory, they match it against their shadow copy, which they keep by emulation. So they really reduce how much they write out the disk. Obviously, things can change, like memory can change in another thread, or your emulation could be not perfect, or it could be floating point, which they didn't do. And they also have these like checkpoint points where they'll stop after every 1,000 instructions or so and say, okay, here's all the registers that we have now. Make sure that everything you have matches this. If it doesn't, resync. So the other question, besides just spitting a bunch of things to memory, is how fast is this going to be? Well, obviously it's going to be slow. It's going to be really slow. But depending on how you do it will dictate how slow it is. Idea number one, the simplest thing you can think of is actually attach a debugger in single step. And that's what a debug run trace will do. Or I guess, I don't know if it still does that. That's the way it used to do it. I think in 2.0 it actually does something a little smarter. But that's not good. You can't run an interactive program like that with any reality. Idea number two is to modify a system simulator like qemu to dump trace information. And this is exactly what BitBlaze, which is the Berkeley guys, that's how they record traces. And their tool is called TEMU. You should check it out. It's pretty neat. Idea number three is this dynamic binary instrumentation I was talking about. So dynamic binary instrumentation, in case you're not sure, it's really cool. It's like an x86 to x86 just-in-time compiler that allows you to modify the code as it's going through the compiler. So you can instrument, as each basic block is about to be executed, you get to pass it through, well, not executed. So it'll start out and you'll get a basic block. And if you haven't seen this basic block before, it'll get passed through an instrumentation function that'll allow you to add things like, record that this basic block was hit, for example, for a coverage tool. And then it'll cache that new instrumented basic block to the side. And anytime it hits that block again, it'll execute that without having to redo the instrumentation. You should check out the Dynamo tool. Where is it? Yeah, so the Dynamo paper from HP is awesome. It's a really good paper, and it explains it all in excruciating detail, but it really answers all your questions, and I think it was written really well. It's really cool. So DBI is used by Dan Reynolds' Trace Surfer, who also just takes a whole trace of stuff. His is for virus unpacking, things like that. So Voidness is implemented as a pin tool, which is this DBI. And pin is the Intel DBI tool. Other ones you might have heard of are Dynamo RIO and Valgrind. Valgrind is still, I think, Unix only. So other things about Voidness, other features. I was talking about those custom watch points. This is how we end up implementing the start to the taint. So while we're tracing the data flow through the program, we need to initialize we need to have some origin for saying that something is tainted or is an input value. So instead of using like read or send, or read or receive or scanf or something that takes input from the system, you can actually do it on a watch point. So you can do it in the middle of a function. So if you know something's already been processed, unencrypted, or decompressed, you can set a watch point there and grab it there instead of having to follow it all the way through the decompression or the decryption. So the other thing it'll do is let you, like I said, start the trace in the middle of the program, and you don't have to take a trace of the entire execution because you might not want all the stuff in the beginning, all the setup from the OS. So okay, the current state is that I don't implement the simulation part that I was talking about that Microsoft had created. I do the caching on the side where you're following the program. So as the program's running, you keep track of the registers, and if a register hasn't changed in between two executions, you don't spit it out, which is really dumb optimization, but you have to do it anyway. And multiple threads are not recorded. They're recorded in separate logs, but there's no sequencing. So there's no way to put them back together right now. I've looked into it a little bit, and that Nirvana paper actually describes how to go about it. So let's look at something. We'll start the demo now. So here's a program we might want to trace. Okay, this is just test 001, and it takes some input on the command line and passes it to a function, and then checks the first 2 bytes of the first argument on the command line. So if the first one is an A, it'll just print 1. And if it's not, then it checks the second one. And if the second character is a B, it'll print 2. Otherwise, it'll print 3. It's a really simple program, just to give an overview of how the tool works. So I think it's already compiled, but I'll make sure. All right. So what we want to do is we want to run this trace capture tool in this. And we're just going to give it AA on the command line, so it falls into this first area right here. But before that, like I said, we have to set those watch points. So what we want to do is we want to mark this. So we want to put a watch point on F and mark A and B as tainted, because that's what we want to follow through the program. So to do that, we're going to open up IDA, which should already be open. Oh. Pretend you don't see that. Okay, there's the test 001 IDB. And we'll go to main here. F, where's main? I'm on a netbook, and I'm not doing so great on it. Okay, here's main. So 2 things we have to capture. One is where we want to start the trace. So we're going to capture this, the address of main, because we'll start capturing at main for this. That's the offset is 41. So where's the Okay. Here's the execution of the voidness trace tool. So we have to execute it through pin, because pin is the DBI that voidness runs under. And we pass it voidness as the tool. And then we say the start module, where we want to start tracing, is this test001.exe. And then the start offset is 11460, which we see here. This was loaded at 400000. And then we pass in the watch point file, which is here. And that's